this on the first day. I didn't put this on this test, but I may put it on the final. I have to and now I forgot how to spell phenomenological. This is why I'm going to take this off the web after Friday. Phenomenological. No. So I can't. Phenomenological models. Remember, I introduced you to a phenomenological model. And before I've used that in true and false to see whether you knew what a phenomenological model was. I didn't in this test. You see I'm giving the answers away. But I might put it on the final. And remember that I started out with the phenomenological model, which was how does a molecule hit a wall? That's a model for pressure because you know that's what generates pressure. That's kind of the point. And what we found was that pressure times volume was energy. You could have just noticed that from the units, which is why I emphasize units. Or, I think the reason I bring that up is I think you've been spoon-fed P equals nRT, and you haven't thought much about it beyond that. But it's really a statement of conservation of energy. Energy equals energy. That's my opinion. Talked a little bit about temperature, I think. I kind of brushed through that real quick. But then we got to, again, we were in high school the first 2 days, and I brought up P versus V. Remember, these were isotherms, which is a perfect 1 over X type of relationship. That would be a low temperature, higher temperature, the same. And so that's, of course, because T is proportional to 1 over V, which is like Boyle's law. I don't expect you to remember that. Also, I don't expect you to remember isocores, which would be P versus T at a certain volume, or isobars, which would be T versus V at a certain pressure. I don't even do that. Remember, this was high school level. Where it got interesting was if you have a lower temperature real gas, which all gases are real, you start to see this non-1 over X behavior and start to see kinks. The kinks look like this. Again, we've gone over that a couple ways. And this is the sign of this is the imperfections of a real gas, or more accurately, real gas behavior. And we then found that these little kinks were due to attractive forces. I'll write down van der Waals equation in a minute. And finite volume. And again, we figured that out with the van der Waals equation. I just want to remind you how a real gas is different than a perfect gas. A perfect gas has the molecules don't have volume, therefore they can't hit each other. That's kind of the consequence that's important. They don't have dipoles, so they don't attract each other. In real gases, of course, the opposite's true. The next thing I went over was how to fit this curve, which is not something I care too much that was the virial. Now, I bring up the virial, and I've asked questions on it in the past because it's just a nice tool to ask questions, essentially. Make sure that you can do some basic algebraic manipulations. I've also asked you, I did an example in class to make sure that you could work the units, make sure you understood the units of B and C were. Remember, B and C were temperature-dependent empirical constants that are just what? What? Yeah. Anyway, okay, thanks. In class, thanks. Sometimes you can find that people carry this Taylor series expansion a little further, whatever. Remember, I use this to also show you how to figure out units, which is on the test as well. And let's see, what else? So I stopped with this, and I think I already told you, and I did. When I have you manipulate real gas equations, I'm actually going to I made up one. It wasn't very virial-like. It was actually more van der Waals-like, and van der Waals is the one I focus on. I may ask you questions about it directly, or again, I have found ways to give you a van der Waals-like equation, but actually made it more simple than the actual van der Waals, and this is the Vm form, where m has been sucked into V. So V over N is Vm. Hopefully you remember that. Just makes everything much easier. And remember that we derived what A and B were. I didn't quite put that on this test. Anyway, we found that at high pressures that the volume was B, which means that B is the volume of a molecule of gas. Approximately, you could work that on a question. We also did it was a low pressure limit. We found that the the van der Waals pressure minus the perfect gas pressure was a negative number, and that says that real gas, the pressure tends to be a little bit smaller than you expect, and that's due to attractive forces. Remember, those were algebraic manipulations. Again, yes, that I had asked you to do that on this test, but I've done so more, instead of figuring out what A and B are of the new equations that I came up with, instead I'm going to go with more of gas imperfection metrics, which were the compression factor and residual volume. Let me remind you, compression factor. You don't really need to do this with VM, you can just do this with volume. Volume of the real gas via the van der Waals equation or via the equation I gave you, which is similar but easier. Divided by the perfect gas volume, and of course the perfect gas volume. V is RT, here the N is gone, P, and here we go. And yeah, there isn't much to say about that. Let's see, what can I do with this? In the case of the van der Waals equation, you see that this can actually be manipulated. So for van der Waals, what equation you derive is, and let's see, I'm not going to do this, I'm just going to give you the answer just because it's relatively easy. I think I actually gave you, I think I did this, I think I gave you the, well, what I can do is just multiply all of this by Vm over RT. I think when I did it in class, just so your notes aren't screwed up, I think I used the Berthelot equation, which is divided by T here. So I'll do van der Waals, which leaves me Vm, so again, I'm just multiplying this thing by Vm over RT. And so the RTs are gone, so it ends up being Vm minus B. Remember, this is a compression factor, which is around 1. Remember, it has no units. And what I end up with, let's see, A, I've got a Vm on top, a Vm on bottom, and an RT. I think, is that correct? Let me double check. Yeah, that's correct. So now, other things I want you to remember, you don't need to memorize this, but you should be able to look at this and figure it out. That compression factors would be 1 for a perfect gas, and I can tell that because if this was a perfect gas, A and B would be 0. And okay, if that's the case, then I got Vm over Vm, and this whole term is gone. I'm left with the number 1. Yes, that is something like that's on the test, by the way. I did get kind of curious to see what kind of questions I could come up with where I turn a real gas equations need to turn into the perfect gas when their A's and B's or whatever are 0. So look for that. And also notice that it does give the number 1, so the natural state of a compression factor is 1, which just means everything's normal. Normal means perfect, P equals nRT. And also notice that there's no units, so liters over liters. Liters per mole, sorry. Liters per mole over liters per mole. So that's the kind of, I'm obsessed with units. Let's see, the next thing we got into in terms of real gas behavior, it's always traditional just to do these two. The other one is residual volume. And the formulas are on the cheat sheet, I just added them. And in this case, it's the volume of the real gas minus the volume of the perfect gas. And sorry, I just screwed up. So remember, this is, I forgot to leave myself. This ends up being quite critical, especially on the question on the test. Remember that there's a limit of P goes to 0. And we also, in the class, at one point you had to use this little formula. Okay, so just remember, if you look at the derivation, you had to use this at one point. I'm going to do that in a minute. And remember that actually when I started talking about residual volume, I actually pointed out that if a gas was a perfect gas, if this was Vm naught, then RT over PVm naught would be by definition 1. But for a real gas, we have to add this limit of pressure going to 0, and that prevents molecules from interacting with each other, either by hitting each other or by dipoling with each other. Neither happens at low pressure limits, so we have to add this to make this equal to 1. for a real gas. Now remember that I started out with them asking whether RT minus PVM was 0, and the answer was no, which is where I get the definition of where I think to ask what is the residual volume. Again, it's not perfect gas behavior. And the way I derive this from the van der Waals equation, what I'll do is I'll take the van der Waals equation, and what I'm going to do is, okay, so I got P. What I'm going to do is multiply that by Vm minus B over P is RT Vm minus B. Now again, I have to multiply by Vm minus B over P minus A over Vm squared. Again, multiplied by Vm minus B. What I've seen people screw up in the past is if I have you do something like this, you forgot this term, you just didn't do anything to it. Remember, multiplication doesn't work that way. So you end up with Vm minus B. And what I'm trying to get to, by the way, is Vm minus RT over P. Anyway, I'm getting there, just to remind you. Okay, now what have I got? I've got, RT over P, right? Yeah, RT over P. Oh, there it is, RT over P. So I just have to switch B and RT over P minus A over VMP plus AB over PVM squared. Sorry, I'm not consistent with P and D. All right, and so now I'm going to do this Vm minus RT over P. Now I'm not going to replace that with Vm naught. I'm just going to go ahead and apply the limit. And the question on the exam, by the way, is much easier than this. And so what you end up with is B minus B is, of course, plus B minus A over RT. And this term ends up being wiped out. So remember what I've done here is I have used this. If you need this, it's on the test if you need it. I know to replace PVM with RT, and that's because if pressure is going to 0, volume is going to infinity, and you don't know how they balance. You can't presume that you know mathematically, but in this case you can because they gave you this. It's RT, which is finite. And remember that this ends up being AB over RT-VM, but that does go to 0 because, again, volume is going to infinity. Again, an equation like this, but easier, expected. It's just algebra, right? It really isn't that bad. I know it seems a little bad, it's not that bad. Okay, again, one of the derivation questions is of this nature. Okay, next, then we got into actual thermo, and you haven't quite seen it yet, but one reason I go over all this stuff is you're going to end up plugging in the van der Waals equation into a lot of thermo derivations. So that's actually the first thing we do next week will be that. So that's why I went over all this. But remember, we started with the equal partition theorem. If you don't mind my shorthand, so equal partition theorem. And remember that defines internal energy, which is the energy a molecule has. Again, a very kind of flip and trite definition that I never quite know what it means, and that's 1/2 RT times the degrees of freedom. And American gases do not actually have more. So of course, this is very fundamental. It's the base of all thermo. If I didn't ask this on the test, that would be insane. Okay, then we need to define degrees of freedom. So DOF. Degrees of freedom are 3 translations. So all gases can translate 3 different directions because we live in 3 dimensions. So that's helium, helium, xenon, argon. That, remember, they can only do that because they can't do what linear molecules are going to add 2 rotations. And that's because you can do this, you can do this, but when it comes to this is no different than helium. This is no different than trying to bowl helium again. It's not real. And then we talked about why that was. Okay, and then nonlinear, and my example is always methane. Nonlinear have 3 rotations, and again, that's 3 dimensions. That's the fact that we live in a 3-dimensional universe kicking in. Now what happens is that I would then kick in vibrations, but we talked about how they're frozen out, and that's a quantum mechanical thing because things do not vibrate more and more as I heat them. What I'm doing right now is false. It does not work this way. Things vibrate a little bit always. It's a 0-point energy, which you've heard hopefully. If not, we're going to cover it in 344, which I expect all of you to be there. And then heat it up, 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 heat it up. It doesn't care. That's why it doesn't participate in thermodynamics. Unless I'm in the interior of a rocket engine, which all of a sudden it does this. But this isn't rocket engine class, that's why I ignore it. So, and you can imagine, yes, this is on the test in some snarky way, degrees of freedom and all that. Okay, now that I've got U defined, U is a function, it has a definition, therefore I should be able to define the change in U, if I'll switch boards at this point. Actually, I think, now I have to admit, I'm kind of blanking on that. Actually, I started with the change in U and then did U by the equal partition theorem, because if I recall, I actually started out with exact and inexact differentials and proved to you what those mean and showed you how exact differentials have functional form, how my little example of f is x dy plus y dx, and how that, the change in f is x change in y plus y change in x, and I showed you that the original function f itself was x times y. But if the change in f was x times change in y, there is no original function. However, that's what work is. F dx is work, force times distance. Anyway, I'm blabbering just because I was erasing the board. So anyway, the change in U, which has to be exact, is heat and work in partial form. And so there you go. And we talked a little bit about why it makes sense that molecules get hit over the head. They don't really care how. Heat and work are really only important to the outside observer. But since that's us, it's kind of important because work is definitely different than heat. We talked about that when we did Carnot cycles and engines. I don't want the fire in my car to produce heat. I want it to produce work, or that would be pretty useless. Let's see, then, so there's one thing we got out of that was that you can define heat capacity as the change in U, as the change in temperature. I'm kind of jumping a little bit ahead. It's just that this is kind of a nice place to do this. Okay, so the change in U with respect to T by the equal partition function would be RT. Oh no, get rid of T. You're doing the derivative. So the T is gone. So you end up with 1/2 R degrees of freedom. And you had to show that that is in fact true for a bunch of gases. I did also point out that sometimes the gases might have degrees of freedom that are a little too high. In other words, nothing's perfect, which would bother me because I live in a world of equal signs. 8.314 is not equal to 8.315. And the answer to the reason that some of those molecules have heat capacities a little bigger than they should is because as they warm up, they actually access more and more degrees of freedom, like vibrations. The problem there is that one requires, remember, rocket engine heat. But I showed you an example of, I think it was acetone was here. I do a different one every year. And that one, this motion actually is not too hard to unthaw, right? Remember that word? It's not too hard to unthaw, and that's why its heat capacity was a little high. And let's see what I want to do with this. Of course, also by the equal partition theorem. So you can see how important it is that the change in U is 0 if the change in temperature is 0. So basically half the questions I could ever ask would be isothermal, the other half adiabatic. So whatever, half are isothermal, change in U is automatically 0. Okay, let's get back to work and heat. And these got a little funky due to packet in this. Now remember, no matter what, test that this is this is the definition of work. And it's got the minus sign for all the reasons I showed you. It just kind of makes sense. I talked a little bit about whether volumes were negative for compressions, or if you're kind of pushing instead of pulling, and then there's a negative sign. Anyway, it's always minus change in exterior pressure dV. And that makes sense because remember, the exterior is where the actor is doing the pushing. Remember, work is only meaningful to the outside observer, but that's us, so it's important. And that's why it makes sense that the exterior pressure is there. And if this is an irreversible case, then the finite change in work, which is of course the partial of work integrated through a definite integral, the minus exterior pressure, again being constant, comes out and you end up with this, which is blindingly easy. And you know I like blindingly easy on tests. Now, if it turns out that you're reversible, then of course what you got to do is you take the exterior and you replace it with the interior. And again, the magic there is just simply because I said I did it that way. Because I slowly, let's do an expansion, I am pushing on the magic cylinder with 2 atmospheres. That's about as much as a person can reasonably push without too much effort. And I slowly back off it as opposed to just jumping aside, which is kind of what I'd rather do. That by definition makes this true. And I end up with, now another big lesson, not on the test, but maybe on the final, is that there's a V inside the P. It's hiding in there. You have to let it come out, or you're doing this completely wrong. So I got nRT over V, and this gives me minus nRT ln dF over di. You do need to use this on one of the 2 calculated questions, actually I think both, but regardless, what do I say about this? Yeah, regardless, I mean there's nothing to it, right? It's just plug and chug. And oh, remember other things. Remember that this is more negative than that one, right? You had lots of homework questions on that, and not much else to really say about this. Yeah, I guess I'm done. And work, sorry, that's work. Again, if I'm still at constant T here, I'm at constant T, so I've asked an isothermal question. You figure out the work, whether it's reversible or irreversible. Of course, these equations are on the cheat sheet. I'll send that to you shortly. You've already figured out the change in U is 0. You figured out the change in work, which now you figure out the change in heat. Put a minus sign on front of that. And now I am not beyond asking you conceptually why this is, excuse me, maybe in a true and false. And of course, the reason is that you know that an expanding gas, if it's not in the Joule-Thomson weirdo device, and I did ask one or two questions on Joule-Thomson. Unless it's in a Joule-Thomson weirdo device, which I tend not to ask about that is a very strange contraption that they built, and it's not like that's the same thing inside a refrigerator. It helps you understand a refrigerator, but that's not how they build them. So I don't worry too much about the devices. So if you're in the magic cylinder device, which is how car engines work and how the power plant works, any gas expanding gets cold adiabatically. So if you're isothermal, then the heat counteracts the work. So in other words, the gas expands, it gets cold, but there's a heat transaction to warm it back up, otherwise it wouldn't be isothermal. If the gas expanded, you know it gets hot, it does, but I said it's isothermal, therefore there's a heat out. And again, it negates the effect of work, as exactly it should. So the equations say that, and inherently it makes sense. Okay, the next thing we got to, we then talked about Legendre transforms, which will be a big part of the second test. You have seen them, but I've got lots of Legendre, this and that for you, but I'm going to save it for the second test. Regardless, it was important because, and the formula is on the cheat sheet. That's when you get your old function, and I told you a little bit about how U has natural variables of volume, and I know that because the change in U is minus P, change in V. And now listen very closely. I'm going to write it down. Well, I have written it down. No, I didn't write it down. Anyway, change in U is equal to blah, 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 change in V. All right, therefore U is a function of V. Change in U is equal to blah, 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 change in V. That means that U depends on V. Now, there may be reasons that I don't like that, in which case what I do is I subtract the dependent variable times the conjugate. That's the blah, blah, blah. It has to be minus P. And so that's U plus PV, just like you've been working with quite a bit. So anyway, so a new energy thing that doesn't depend on volume, but now depends on the conjugate of volume, which is what appears by volume, which is pressure. So enthalpy depends on pressure. That does mean something. Remember that enthalpy ends up being heat at constant pressure, just like U. The change in U was the change in work at constant volume. Now that makes sense because if there's at constant volume, there's no work because we're only going to do gases. Therefore, the change in U is the change in heat at constant volume. That's really useful because all engines begin with a burn. We live in a heated society, so I really need to understand heat. But again, we don't build machines that work at constant volume. We do sometimes, but they are obscenely dangerous. Most of society, our machines are processes that occur outside. That thing that happens in a beaker, cells interacting with each other occur at constant pressure. And that means that H is heat under constant pressure. And the Legendre transform does that. Now, of course, we're at constant temperature. I've asked you to do a gas expands, a gas contracts. You've already figured out the change in U is 0. You hopefully remembered that. If not, you looked at the cheat sheet and saw the equipartition theorem. Okay, the change in change in H would be the change in U plus the change in P times V, which is actually normally kind of difficult, especially if P and V are changing simultaneously, which is often the case. I did give you one example where I was able to build a weird device that violated that, but for the most part, if P and V are changing, this ends up really being kind of impossible. And so what you do is you just switch that with NR change in T by the perfect gas. A hint to do that is I would have told you that it's a perfect gas. Or you could assume it, but on the test I'm pretty careful. And I've already established that at constant T, change in U is 0, the change in T is 0 by definition, and the change in H is still 0. So don't forget, if you miss a lot of units, I will dock off a point, but only a point because they're not that bad. Okay, now I'm actually kind of going out of order here because I'm hoping that this makes a bit more sense. But as we kind of slid into adiabatic transitions, I can't pronounce that. Actually, I started out with talking about something that sounds very thermo-y, which is heating a gas, and I would have had to have wrapped it in glass wool. Otherwise, the heat would have just escaped, and what's the point? Now, I don't know how I would have added heat. I guess I could have inserted some wires into the device around the glass wool and just added some juice and it would have heated up. And now I want to know about that because that's whatever. Heat transactions, remember, are adiabatic. Just like, I'm sorry to go off on a tangent. On these gas expands and gas contracts, remember, we're going to do a lot more of these and they get a lot harder next week. I actually, just so it's just less painful, I will actually ask you to give me the variables in order in which you need to calculate them. If I say an isothermal, the first thing I ask is what's delta T, right? And hopefully get that very quickly. If it's adiabatic, I will first say what's the change in heat. What's the heat exchange? Of course, the answer is 0. Now, it still heats up because, again, I've put in wires around the glass wool and hit some juice so it got hot. Now remember that adiabatic, this is the one I did with the graph. How do I figure out what to do next? I've got one of my 5 or 6 thermodynamic variables. I've got 5 or 6 more. How do I get to them? I did this with a graph. You have actually 3 graph questions because some of you are good at this and I have this for you. If not, then don't do them, or maybe they're just inherently easy. But anyway, this is one of the times that I did the calculation or derivation or whatever with a graph, and I did an expansion, which of course would cool the gas, and I said, okay, what can I come up with next? I guess the change in U. Why not? Change in U. And I didn't know what to do until I made this graph, and of course, temperature, and I know that U is not going to, the change in U will not be 0 because I'm changing temperature. And that's how I know that, unlike isothermal, I am going to actually not get a 0 for a change in U like I did isothermally, again, because the temperature is changing. And the cleverness was to remember that the change in U is exact, and therefore I can not only go down any path, I can analyze this any which way I want. I can even analyze it in ways in which it did not actually occur, as long as I appear at the as long as I start in at the right steps. I can even go down paths that are unphysical, like this case. I've expanded the gas, but I kept the temperature constant, and therefore the change in U was 0. The change in U, of course, is this leg plus this leg. And so U2 is, you see, this is why this is fantasy. If I expand something, it's kind of cool, but I said it wasn't. And then I take that into account in the next step. At constant volume, I drop temperature, and I know that the energetic consequences, again, I'm at constant volume, CV dt. Now, remember that for something where the formal heat transaction is 0, I certainly see CV. I see CV in everything, right? And that's kind of weird because normally I associate CV with heat dq. It's 0, yet everything has CV in it. And again, that's just whatever. Well, I guess this is the proof. Okay, so now what? Okay, so the change in, so I was trying to do the change in U, which is the change in work plus the change in heat. But I defined that to be 0. I just showed you that actually it is CV dt. Don't forget that you actually need to take what I give you, which will be the heat capacity per mole, and multiply it by number of moles. This is how you'll figure out the change in temperature, and that's where you get everything else. Now, since this is still work, it's still work because remember, I canceled out heat. This is still true. And now you have an avenue to figure out what the change in temperature is. So remember, you might think that I could use PV equals nRT. The problem is I got PV and T changing. That used to not be true. T was constant because it was isothermal. So this is the route by which I will use. PV equals nRT still works, but I have to find another way because I can't practically use it. This is my way to figure out the change in temperature. Integrate this if you're irreversible, and you know what that leads to, a bloody CV delta T is minus exterior pressure delta V. It looks deceptively easy. It's actually horrible because you did that on your last homework, and I think I'll have to do it one more time. I'm not leaning for that on the test. Reversible is actually slightly easier. And remember that, so I'm not going to write down, well, I already told you what irreversible is. Reversible is a little bit more interesting. Again, I'm going to put in interior pressure, NR, I'm going to bring the T over here, and bring the V here. Okay, and then of course I need to integrate both of them because, don't forget, I'm trying to get that final temperature. And what I end up with is, I'm going to skip some steps here because I've already done this, and you even had a handout on it, and I've already absorbed the minus sign. I always, now you don't have to remember this, this is on the cheat sheet, but I remember that the T's and V's are actually always flipped with respect to each other. And therefore, again, I'm just going to skip some steps. I have put this derivation on the test before, or a variation maybe with pressure as opposed to volume, something like that. I did not do that on this test, but I could put it on the final. I can think of a test, a question I'm thinking of putting on the next test where you do need to be able to do this. It's in a different context, but anyway, okay, and the last bit that I could possibly ask of all the gas expands and gas contracts. Okay, so sorry, so now you got your final temperature, now you got the change in U, you get the change in H, it's the change in U plus NR change in T, and that's it. Not quite, because last time I covered the change in entropy, and yes, I did ask this on one question, and the formula, again, is in the cheat sheet. I'm not going to say too much, I'm a little hesitant because I didn't put it on the homework yet. But the change in entropy is the change in heat over temperature. And it just turns out that, well, therefore, I got to integrate it. And what I get with, if I consider a isothermal transition, I know that I can take the heat and plug in the negative work. And so that ends up being minus nRT, except I got a minus divided by T, so it's nR ln VF over VI. I showed you that there were two ways to derive that. Whatever, there it is. Okay, that's isothermal, but if I wasn't isothermal, I would need to think about that heat transaction, even though it's formally zero. Again, this is, we keep seeing CV show up, and you end up with ln TF over TI. So the cheat sheet has this equation, and it's fine because remember, this being a state variable, it works under any circumstance, right? If you're isothermal, this term will be zero. Let me give you another example, change in H. See, now remember, these are state variables. They don't care what path they went down. This is one of the ways you would calculate the change in H. Notice that if you're isothermal, it's zero, right? Just like the change in U is CV delta T. Again, isothermal, U's and H's are zero. What this equation says that if you're adiabatic, they're not zero. It's still the same formula. State functions have the same formula. It doesn't care what happened. Even if there is a subtlety, like if you're isothermal, you can still plug this in there. It just wipes itself out. You don't have to think about it. It makes life easier. Okay, last bit, and we're going to end a little bit early. I can answer questions and actually get back your homework on time. We then got into Joule and Joule-Thomson Carnot. Now, Carnot is a Bismarcker to derive. I didn't really derive it. I don't know that that's the proper word. It's just a mess of stuff.
Someone has a question.
Question?
I have a question.
Yeah.
So over there when you wrote delta, change in U over change in V, keeping T constant, that's equal to CV, right?
Change in U with respect to temperature at constant volume is CV.
Okay.
That by definition.
Yeah, so then also in our notes, how come we have change in U over change in volume with T constant, that goes to zero? And remember
well, okay, so actually let me get into that in a second. That is going to come up in a derivation.
That's
right?
only when you're trying to derive it, right?
Well, okay, I'm going to answer your question. So trust me.
Okay.
Trust me.
Because like it's equal to CV, but then it's equal.
No, it's not. You said the change in U with respect to volume. That is not CV. CV is changing U with respect to temperature.
Yeah.
You got your T and V switched. You see what you did?
No, but I still have T in my notes.
No. Well,
so it's
that might
constant volume is zero.
Wait. Okay. change in U, change in T at constant V is CV.
Yeah.
Not zero. Change in U, change in V at constant T is something small, if not zero.
Okay.
Yeah, you got your T and V.
Okay. Sorry. Thank you.
No, that's fine. That's fine. Other people, no, some of you did that at office hours. So, okay. So Joule and Joule-Thomson, and then Carnot cycle, and I've got about almost 10 minutes. Carnot, I won't say too much about. It appears in a true and false question because remember that was a giant. It wasn't a derivation. It was a giant mess, and I just had to put it all together, and it was really confusing and detailed. The first time I ever taught the class, I got it completely wrong. So I can think of a good. That is great for explaining words. But I am not going to ask you to derive the efficiency because it took me pretty much the entire lecture to do that, even with a good set of notes. So I won't say too much about Carnot, but let's do Joule and Joule-Thomson. So Joule and Joule-Thomson. We're all about determining how temperature changes with respect to volume at constant U, and how temperature could change with respect to pressure at constant H. Now, I often see U's with V's and H's with P's because those are the natural variables. It doesn't have to be that way. I can certainly ask how T changes with P at constant U, and I can build a crazy device to do that. It's just I generally just don't want to. And what this ends up being, what is useful about this, does appear at least 1 or 2 times on the test. Forget the crazy mousetraps. What this is really more about is derivations, and you do have a derivation. And remember that all derivations come down to this. And so this is really, really important. It appears at least twice on your test. And of course, this is in the cheat sheet. So anyway, so you don't have to remember it, even if you, I mean, hopefully, I'm going to have you work this so many times that you notice I'm not even looking at my notes, I'm just sick of this myself. So all derivations are basically going to start with this, and then you do more stuff, and that stuff often ends up with a du dv at constant t, and that for a perfect gas would be 0. Or you end up with dt at constant anything, which is 1. Now we went over that, how that often shows up. That is going to appear on the test. And yeah, I didn't really have much else to say about that, just that if you get confused, remember, if I'm asking like the change in H with respect to something, H, and then I say, what's the change with respect to T at constant pressure? There's your T. Okay, there's your T. Constant pressure is here. Now remember that if I switch temperature at constant pressure, then I am obliged by definition to do the opposite here, right? You have to do that. So again, that's how you work all of these derivation questions. And then you do some simplification. du dt at constant v is Cv. Du dv at constant t is 0 if it's a perfect gas. Yeah, there's really not much. After you get past this, it's all algebra. So I don't want to say too much about that. The last thing, again, to bring up Carnot cycle, I just want to remind you that what was kind of neat was this idea of a reciprocating engine, which again is a practical thing. I could build cars with wind-up springs, except that would just suck. So Carnot knew that you needed a crankshaft. He knew that it has to start where it ended, and that this was this cycle results in a stall. So what he figured out was that the compression stroke has to occur at a lower temperature. And when you do that, the positive work of the compression is not going to negate the negative work of expansion. Again, a practical thing. Expansion work is work out because we build devices to push us, not pull us. Again, think about how would you practically design a car that instead of pushing up on the crankshaft, the power stroke, what if it could push down? It should be possible, I just don't know practically how. Push up, power stroke is easy, that's burning gas. Opposite, I don't have a clue. Remember that a percent efficiency is 1 minus T cold. Again, through a half an hour of messing around with all the works and heats and yada, 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 I derived that. But the purpose is that all machines do not turn all heat to work. Okay, unless the tailpipe is at absolute 0, which you can't do, which you learned in 44. Yeah, that's really all I got. I've actually given the answer to several questions while I've been talking. Any of you have any questions? Anything else I can do? Last going? Okay, send me some.